Hi, I'm Dennis, and in this video I'll show you how I made this Geisha figure on a 3D scroll out of 4 different types of natural unstained woods and carbon steel epoxy resin. I originally planned to use the traditional CNC inlay technique, but I ran into several technical issues, which I solved with a new optimized prism technique for very precise inlays. The inlay technique has been around for quite a while. It is based on carving a pocket shape, also called female, into a board and then a mirrored protruding shape, also called male, that is usually carved out of wood with a contrasting color. This male piece is glued into the pocket and the excess wood is removed to reveal the shape, a bit like those wooden puzzles for little kids. But you can immediately see the problem at the corners when using a straight end mill. You can cheat a bit with simple forms by rounding the corners, but that won't work for sharp angles or lines that are thinner than the diameter of the bit, as the bit just can't get to those areas. So some clever techniques have been developed that make use of a V-bit instead of a flat-tipped end mill, which allows the creation of sharp corners for more detailed patterns. Now, I checked out several of those traditional inlay techniques, but most of them apply a V-bit toolpath to both the female and male components, and that brings some technical problems. And if you do not understand the problem, you cannot appreciate the solution. Right. So let me explain. One of the problems is that we have to use an aggressive bit plunge to trace the mill shape, by tricking VCarve into thinking that the shape to be carved is below the actual stock surface, so that the mill shape is sloped, and the longer the slope, the deeper the mill can sink into the female VCarve. Let's say we want to make an inlay in the shape of the blue oval with a 60-degree V-bit. Looking at it from the side, a cross-section of the female stock would look like this, with the blue lines representing the oval's edge. The maximum depth of a 60-degree V-bit would be 5.5 mm, and the V-pocket would look like this. If we then want to carve a mirrored male shape, using the VCarve tool with the same bit and maximum depth, the male would look like this. However, that male would not fit. What we need is a male that looks like this, and we probably want to add some space between the male and female surface for the glue to flow into, and maybe a bandsaw to fit in between, which means that the edge of the oval shape needs to be on the slope at about 1/3 from the bottom. So we need to make the bit perform a V-carve following this shape, and go this deep. And the only way to do that with the software right now is by telling the bit to start carving at this depth and go this deep for a combined depth of 5.5 mm, as that is the maximum angular cutting depth of a 1/4 inch V-bit with a 60-degree tip. And then use a flat end mill to clean up the large surfaces. Okay, problem solved, right? Well, not exactly. Let's recap and have a close look at what we just learned, and then see what happens if we apply these different techniques to a more complicated shape. If we want to make a diamond shape inlay and use a straight end mill to carve both the female and male, the round female corners won't accept the sharp male corners. Using a 60-degree V-bit to trace the profiles won't work either, as the contour of the male plateau will be exactly the same size as the ledge of the female pocket, so the male can't sink in. Combining the same female V-carve with an extra deep male cut will work for a simple diamond shape like this, as the male can sink in, but only up to the point where the sharp corners transition to a curve. However, when the shape becomes more complicated and has narrow grooves, like my logo, then we run into other problems. The female can be carved with a 60-degree V-bit as usual, and an end mill to clean up the large surface areas of the pockets, but creating the male with this deep V-carve will result in very shallow contact, and therefore a small gluing surface area due to the thin grooves. Also, some of the individual shapes are so close to each other that the V-bit can't squeeze in between to clear out enough material. The deep male V-carve is basically not an exact inverted copy of the female V-carve. But the prism tool is. This is most obvious from the letters, which are shallow and high up in the female, while short and at the very bottom of the male. Another example is the centers of the triangles that are deep in the female, while tall and reaching all the way to the very top of the male. So the female and male shapes are now exact inverted copies of each other, but the male still has a lot of material that needs to be removed because the prism tool does not have an integrated cleanup option like the VCarve tool. So I hope Vectric is watching this video, because the cleanup is not so straightforward if you have to design those toolpaths manually. We have to add a separate cleanup toolpath for which we can use the standard pocket tool, and we can select multiple diameters of bits to reduce the total carving time. But to keep this example simple, I picked only the smallest end mill that I have, which is a 1/8 bit. So the female V-carve setup remains unchanged, but the male prism carve is now followed by a pocket cleanup. But when you look closely, you can see that the end mill cannot get into those tight corners, so we need to clean up these with the V-bit. When drawing that smallest end mill, which is the 1/8 bit, into the design, you can see that it varies how far the bit can get into the corners, as it depends on the angle of the corner. In the worst case scenario, the bit is kept out of the corner by its radius perpendicular to the closest wall. Or in other words, we'll need to create an offset trench around the shape that is as wide as half the diameter of the smallest cleanup end mill that we're using. And in this example, that's a 1/8 bit, which has a radius of 1.59 millimeters. I'll round this up to 1.6 millimeters for ease of calculation. When we run a V-carve in this trench, looking at it from the side, you can see that the deepest that the 60-degree V-bit can enter before its slopes touch the trench outline is 1.375 millimeters, which I will round up to 1.4 millimeters. Now we also need to keep in mind that this V-carve cleanup needs to start at the very bottom of the mill, which is 5.5 millimeters at its deepest point. Since most of the material has already been removed, I'm not too worried about such a deep plunge. The CNC and bits should have no problem handling that little bit of wood. Now, if we would fit the male into the female, it would look something like this. And in that case, we might as well deepen the cleanup cut with the end mill by 1.4 millimeters to a total depth of 6.9 millimeters to match a trench depth. This will also create some extra space for any glue that is squeezed out and a bandsaw to fit in between. If we then also shave off another 0.6 millimeters from the top of the male, then we'll have our glue space at the bottom of the female too. And considering that some male ridges will be very thin and fragile, we might want to do this shaving step at the very beginning of the male carving process, as long as we remember to retain the original Z-start height where the surface used to be for all our following carves. My experience is that wood needs about 0.2 millimeters of wiggle room on each side for a tight press fit. So if the male slopes end up at a perpendicular distance of 0.2 millimeters from the female slopes, then the distance between the horizontal surfaces will be 1.8 millimeters, which would be enough for most bandsaws, and 1.0 millimeters for the glue that is squeezed down from the slopes into the female pockets. When comparing the two techniques side by side, you can see that the traditional deep V-carve approach will work, but that the optimized V-prism carve of the male is almost an exact inverted copy of the female and fits much better. At least that's a theory. We'll find out if it works in practice. But before I bore you to death with more toolpath talk, let's first have a look at the design and the materials that I chose. About 2 years ago, I made this Geisha figure using a standard V-carve technique, and I thought it would be nice to make a new version out of it, but then with color. Now I love the texture and grain pattern of natural wood in all its imperfections that give it some extra character. So instead of staining or painting the wood, I plan to use different types of wood with distinct natural colors. I want to create the impression of a traditional Japanese scroll painting for this project. American holly is one of the widest hardwoods, and I will use this for the background of the scroll and the fans. Hard maple is slightly darker and has more of a tan color, so I'll use this for the skin. Padauk has a natural deep red color, which will be perfect for the kimono and the mouth, as well as some other fine details. Olive wood has a very distinct wavy grain pattern of darker and lighter caramel colored lines, which can mimic the reflections of the golden embroidery on the kimono and some other decorative elements. And all these inlays will be traced by a thin line of sparkling carbon steel epoxy resin. Now let me show you how I designed the toolpath using the optimized V-prism technique that I explained. I set the job dimensions to 177 by 625 millimeters with a thickness of 18 millimeters. Instead of creating mirrored copies, it's easier to change it to a double-sided project, and then design all the female carves on the top and male carves on the bottom. But this is only to make the design process easier. The female and male components will be carved from different pieces of wood. I imported the drawing and traced both sides of the black lines with vectors. the actual stock will be larger, so it's okay that the lines are very close to the edge. After manually cleaning up small isolated vectors and closing gaps in the contours, I grouped vectors of areas that would be carved out of hard maple and copied the combined vectors to new layers with name and colors that match the types of wood. I repeated the steps for Padauk, olive, and the epoxy lines, to which I added the characters for Geisha. Going back to the hard maple, I created an outwards offset trench of 1.6 mm without sharp corners, as the smallest cleanup end mill would be 1/8 of an inch, which has a radius of 1.5875 mm that I rounded up to 1.6 mm. I grouped the offset trench and moved it to a new layer with a distinct color. I copied both vector groups to the other side to create a mirrored image. I flipped to the bottom side as the mill needed one more vector for the shaving and clearance toolpaths, both of which can use the same vector. Since I plan to use a 1/1/8 inch surfacing bit, I created an offset of 30 mm around the hard maple contour, as the diameter of that bit is slightly smaller than that. I moved the vector group to a new layer and gave it a different color. I flipped back to the female side and removed the offset trench, as that is not needed for the female V-carve. I switched to the toolpath commands, kept the start depth at 0 and changed the flat depth to 5.5 mm, as I plan to use a 60-degree V-bit combined with 1/8 and 1/4 inch end mills for clearing out the large areas. V-carve automatically selects an offset direction, and I made sure it was set to climb. I usually apply a ram plunge that is twice the diameter of the largest end mill. After calculating the toolpaths, I changed the names so I know which tools are required. And checked the simulated carves. I then flipped to the mill on the bottom side and selected the cleanup vector for the 0.6 mm shaving step, for which I chose my largest bit, which is the 1/1/8 surfacing bit. I also included a ram plunge of about twice its diameter, renamed the toolpath, and checked the simulated carve. I selected the hard maple contours for the prism carve, which should be carved at 5.5 mm, using the same 60-degree V-bit as was used for the female V-carve. I chose a climbing toolpath, named it accordingly, and checked the simulation. After that, I selected the hard maple contours and a cleanup vector to remove the material around the prism carve. I chose the same tools and settings as I did for cleaning up the female V-carve, but set the depth to 6.9 mm. Finally, I selected the hard maple contours and the offset trench to remove the material in the areas that cannot be reached by the end mills, with the V-carve starting depth at 5.5 mm and cutting 1.4 mm deep, using the same 60-degree V-bit. I had purchased a piece of 150 by 300 mm hard maple stock. To visualize this, I added a new layer, drew the dimensions and centered it. I then selected all male carves and centered these as well, so I could make sure that everything would fit. It would also make it easier to accurately position the stock onto the CNC bed. I recalculated all male carves and saved them as Gcode files. The simulation also shows exactly where I can clamp the stock down and the surfaces that I can use to reset the Z height after swapping bits. For clarity, I added matching colors to the different toolpaths. I repeated all these steps for the female and male carves of the Padauk. I did the same for the olive female carve, but split the male carves into 3 separate jobs, as the pieces of olive wood were not big enough to fit all carves. Last was the female carve for epoxy, which does not have a male counterpart. Alright, enough talk. Let's get started. First, I'm going to make this board of American holly half the length and twice as wide. I cut it in half, jointed the sides, and glued the 2 halves together. While the glue is drying, I can start with the first male inlay, hard maple. Even though the stock is about double the thickness I need, I'm not going to make it any thinner before the CNC process. Because if the optimized V-prism inlay technique doesn't work, or something goes wrong for whatever reason, I can always surface it with a planer and start over again. The reason why I'm doing the male carves first is that this is a multi-inlay project, and all the individual female carves need to be precisely positioned relative to each other. Also, each new inlay is followed by a surfacing step before the next female V-carve. And I would never be able to achieve that kind of precision if I first had to remove the female stock to carve the male stock and then put the female stock back again for each consecutive inlay. I cut the piece of hard maple in half and marked the center. After clamping the stock down, I checked the cutting area in VCarve and repositioned the clamps accordingly. I used a V-bit to set the X and Y 0 coordinates to the approximate center of the stock. I first used a servicing bit to shave off 0.6 mm. Then swapped it for a 60-degree V-bit to do the prism carve. After that, I used a 1/4 inch end mill to clean up the large areas, and then a 1/8 end mill for the areas that didn't fit the 1/4 inch bit. Finally, I used the same V-bit again to carve the offset trench. I'm quite satisfied with how crisp the edges are. It looks like there's very little manual cleanup to be done. Hard maple is done, Padauk is next. The CNC process was the same as for the hard maple. The Padauk is done too, so now the 3 pieces of olive wood. The high density of olive wood makes it an excellent material for fine details. All the male carves are completed and the glue of the American holly has dried, so now I can prepare this for the female carves. I scraped off the glue that had squeezed out of the seam and planed both sides to make it as flat as possible and give it a uniform thickness. Although I don't mind some imperfections in figured wood, this blemish here stands out a little bit too much on such light and smooth looking wood. But if I keep it on the left side, then it should be covered underneath the inlay. The board is practically flat, but I still need to surface it with the CNC to make sure that it's completely level relative to the router. So just like the male carves, I surfaced the American holly by shaving off a fraction of the top layer, and then proceeded with the female V-carve, followed by the cleanup. Very small inlays like these will be challenging, so instead of gluing the whole panel, I will cut it into smaller pieces with the bandsaw for more precise positioning of the individual male inlays. The moment of truth. Looks like it fits. Let's get this glued in. I put the glue on the male inlays, pushed them into the female pockets and secured them with the clamps. I'm going to let it dry overnight. The glue has dried, so now I can remove the excess of the male inlay. The back of the male stuck out almost 15 mm above the American holly surface. I reset the Z0 to 16 mm above the stock surface and then removed 15.5 mm, so there was about half a millimeter of male inlay still sticking out above the American holly surface. This should be low enough to allow the other male inlays to completely sink in. Some of the male inlays were too thin and fragile and broke off during the CNC process. I'll go ahead and see how it turns out. If the female pockets are filled with just glue, I'll recarve only those areas and then manually fill them with a mixture of sawdust and wood glue. To reduce the CNC time, I removed several millimeters from the back of the Padauk mill with the planer and roughly cut out the shapes with the bandsaw. I then carved the female pocket for the Padauk. Even though I worked as fast as I could, the glue already started to dry in the areas that I had spread out, and I was unable to push the male inlay all the way down into the female pocket. So next time I'll divide large areas like these into smaller pieces that I can glue in separately. After removing the excess male, I saved some sawdust to fill the gaps later on, and carefully vacuumed the rest, after which it was clear that the left side had not reached full depth, while the right side had. Because the olive wood panels were too small for the planer, I used a jointer to remove the material from the male back sides. After carving the female pockets for the olive inlays, I decided to put the glue in these pockets instead of on the male inlays. That worked out much better. I collected sawdust from every single carve so I can make some small repairs. I put a drop of wood glue in the gaps that were missing inlays, sprinkled a generous amount of matching sawdust on top of it, then firmly pressed it in and let it dry overnight. And last is the V-carve for the epoxy. I used clear epoxy resin from the Epoxy Resin Store and mixed in the carbon steel mica powder. I used a chopstick to drip the epoxy into the V-carve grooves. It will take the epoxy about 3 days to be hard enough for resurfacing. The epoxy is now hard enough, and I initially planned to do the final surfacing step with the CNC, but I'm afraid that the bit will leave burn marks on the white American holly. Sanding is definitely not an option, because the red dust from a Padauk will for sure leave stains all over the place. So I'm going to use the planer. I checked the difference in height, and it looks like the CNC bed is level enough and not tilted or warped, so I'm just going to hope for the best. After several light passes, the top and bottom side were in pretty good shape, but I noticed that the midsection still needed a little bit more shaving. Apparently the CNC bed was not flat enough. If I would simply continue to lower the planer, the knives would take off too much from the top and bottom, so I lowered the planer only in the center and then quickly moved it up again in a fluent motion as the board was pulled through. To create the impression of a scroll, I will add 3D rolls to the top and bottom. And although inlays are technically speaking 3D cuts, those rolls are the only two parts that will truly look 3D. I'll make them out of 2 boards of American holly and a piece of olive wood. I jointed one side of each board, rid them with the table saw, and then glued the halves for a combined thickness of just over 50 mm. I let the glue dry overnight. In the meantime, I designed the scrolls in Meshmixer and a toolpath as a double-sided job in VCarve. I added 2 stubs to the bottom for alignment when flipping the stock, similar to the vertical tabs that I explained in my video where I carve a frog on a leaf. I then used the Moulding tool in VCarve to design both sides of the end caps that would slide over the poles of the scroll rolls. Since I added dowel holes to the double-sided design, I secured a piece of spoil board on the CNC bed and mounted the olive wood stock on top. I cut the tabs with the bandsaw, removed the stubs with the Dremel, and then finished it off with the file and sanding paper. After the glue of the scroll stock had dried, I clamped it onto the CNC bed as straight as possible to first carve the bottom side. I had added these alignment stubs to the design for precise positioning when flipping the stock. I then secured 2 pieces of spoil board onto the CNC bed, lowered their centers to a 4 mm thickness, and carved the alignment holes that fit the stubs that I had carved on the bottom side of the scroll. I cut the alignment stubs with a flush cut pull saw and the tabs with the regular fine tooth saw, and then finished the surface with sanding paper. I added a few drops of glue onto the scroll ends and slid the olive wood end caps on. While the glue was drying, I cut the top and bottom ends of the completed inlay with a 20-degree angle. I stuck painter's tape to the backside of the inlay, put a layer of wood glue on the surfaces, and wrapped the tape around the scroll to hold it in place. After the glue had dried, I covered the wood with a single layer of clear varnish to preserve the natural colors of the different kinds of wood. Now that the varnish is dry, let me point out a few things that didn't quite go as planned and what I will do differently next time for better results. First of all, I will avoid very thin mill inlays, as the wood will be very fragile and is likely to splinter and break off. This means I will have to make some manual modifications to the design in VCarve. Especially the Padauk was not really cooperating, so next time I'm working with large inlays, I will subdivide these into smaller separate inlays for easier handling and less warping of the wood. I will also use slow curing glue instead of regular wood glue to give the male inlay more time to completely settle into the female pocket before the glue gets too hard. You may have noticed that for hard maple and Padauk, I put the glue on a male inlay, but for olive wood, I put the glue in a female pocket. Putting the glue in the female pocket resulted in better distribution of the glue on the slopes and fewer issues with air bubbles. Although I'm glad I decided to use the planer instead of sanding paper to make the male inlays flush, I had to dynamically change the planing depth while the wood was being pulled through the planer, because the inlays did not have a uniform depth, which is probably due to the CNC bed not being exactly flat and level. All in all, the optimized prism technique for inlays is very accurate, and the issues that I ran into are more dependent on the procedures that I tried and the properties of wood than the technique itself. So that's it. Thank you for watching.